Okay guys, I got quite addicted to the new simulation nodes in Blender, so it's time to do a new tutorial about it. Today we're going to create this splattering paint cannon system that we're going to create with 3 simulation zones. And by the way, this Blender file that I'm going to use, you can find that on my website mtranimation.com, and that's also the place where you can find all the previous project files from previous videos that I've uploaded. With that being said, let's jump right into it. I've created this setup for the tutorial. First I added in a plane where the particles are going to interact with, and I've also added in 2 empties which are going to control like the direction of the particles. This one I called that shooter empty because this one is going to shoot the particles, and this one is the direction empty because that's where the particles should go to. Then I've also added in this cube, and this cube is going to be the object with the actual geometry nodes on it. So let's click on the cube, go into the geometry nodes and click on new to add in a new geometry nodes. We don't need the cube, so we're going to remove the group input, and if you press Shift A we can start off with points. This points node, if we connect it with the group input, then you see we're getting a point on the place where the cube was. We want that this point is always at the same position as our shooter empty. So we can drag in our shooter empty right over here into the geometry nodes. And to make it that it's on the same position, we want to do a set position node, and as the offset we do the location of this shooter empty. And you see it's not on the same position as the empty, of course. That's because we have to say that we have to make it that the position of the actual, like the previous cube, that's 0, 0, 0. So go to the object properties and go into location, hover with your mouse over it and press backspace. And then you see it will always be on the same position as the empty. From here we're going to add in our simulation zone. So let's Shift A and do simulation zone. Connect the set position into the simulation input and the simulation output to the group output. Let's create a beginning velocity for our point by clicking on the simulation input. Click on N to make this pop-up open. Click on plus to add in a new attribute for our simulation and name this velocity. We don't want this to be geometry, we want it to be a vector. And if you're now in the simulation input, if you make that velocity, if you make it like 0.01 or something like that, and you start playing, then you see nothing happens. You have to connect the velocity to the end velocity, plus we also have to do a set position node in order to make the point actually move. So in the offset, set the velocity, and then you will see it will start rising every frame by a factor of 0.01. But let's make this beginning velocity 0 actually. I want to make it that this point is traveling towards our direction empty. So we want to determine the vector that goes from this empty to that empty, so that we have the direction. To do this, add in a position node, so that we have the position of the point, and also drag in the direction empty from the collection into the geometry nodes. To get the vector, we want to use a vector math node, set this from add to subtract, and subtract both positions from each other. Now in order to make it not go into oblivion, we are going to normalize this vector. So Shift D on the subtract node, set this on normalize and connect it like this. Now we want to add in the vector that we've just calculated to our original velocity. So let's add in another vector math node and let's connect it like this. Now if you press play, you see it goes very fast backwards. 2 things we've got to do. Let's make it slower and let's make it go to the other side. So let's Shift D this vector math node and set it from normalize to scale and connect that before the add node. Set the scaling on -1 so that it goes reversed. So now you will see it goes like that. Let's make the speed of the particle go a little bit slower by taking this scaling node and Shift D it and place it over here. And let's set the scale on 0.01. And then you see it goes a lot slower. Let's actually set it on 0.001. A few problems that we're having is it wants to go like to it as if it has gravity, but we don't want that. We want that after the particle has been shooted, that the particle will not be affected by the movement of the empty anymore and that it stays in its direction. So to do this, what we can do is we can remove this add node actually, and I'm going to move this all the way over there. And we want to add in a mix node and set this from float to vector. And we want to say, okay, vector A is going to be the original velocity. Vector B is going to be the direction towards that empty. And as the vector, we want to say, okay, if the point has a velocity of 0, so if it has not been shooted yet, then it should get the direction towards the empty. But if it has already been shooted, so if the velocity is not 0, 0, 0, it should keep its velocity and not change at all. So let's add in a compare node to do this. And let's set this from float to vector. And set the result into the vector of the mix node and the velocity into vector A again. As vector A, we want to say, okay, if the velocity is equal to 0, 0, 0, then it should become this one, and otherwise it's going to keep its velocity as it is. You now connect this with the velocity. You will see, oh, let me speed it up a little bit, like 0.01. You will see that while it's traveling, it's not being affected by the position of the empty anymore. I don't just want to shoot one point, no, I want to shoot a lot of points. Like at the moment, I would like to add in a new point every single frame. And we can do this by adding in a join geometry node, add that before the set position, and put the other set position into the join geometry, and then you're getting this. I'm going to speed it up even more. Let's set it on 0.1 then. That's better. And then you see we're getting a cool shooting effect. Let's add in some gravity, right? Because now it's going like into outer space, but I want that there's some gravity going on. Very easy to do. Let's add in a vector. And this vector, we're going to set the z-axis on minus 9.81, like gravity. And then we're going to say, okay, with a vector math node, we want to add this gravity into our original speed. And then that goes like this. It goes way too strong, of course. So let's take this add node, put that over here, set it to scaling, and set the scaling on 0.001. And then you're getting this. And if you go back to the vector that we've created before, if you set this scaling on a higher number, like 0.3, then you will see it goes like faster. And it would be cool if we have like a controller for that. So what I think would be cool if we take the scaling of the direction empty, and if it's like, if the scaling is bigger, it should go faster. If it's smaller, it should go slower. So to do this, we can go back into the geometry nodes, and we have the scaling of that empty over here. We can just connect it with the scaling. And now if you make this smaller, you will see I have control over the beginning speed of our particles. Obviously, it doesn't really look good if we shoot a point every single frame. I think it would look better if we choose randomly which frame is going to shoot a point. So to do this, we're going to add in a delete geometry node between the join geometry and the set position over here. And as the selection, we want to say a random value. This random value, set this from float to boolean, then you can set a probability. And if you put it now over here, then it's going to be the same probability for each frame. But if you set the seed value to be dependent on the scene time, like this, then you will see it will start choosing randomly which frame is going to shoot points. And if you set the probability higher, there will be less points. And if you set the probability lower, there will be more points. I will set it on like 0.8, something like that. I want to delete the points if they are colliding with my plane over here. So to do this, we want to determine when is the distance between each point with the plane lower than a certain value. And if it's lower than a certain value, delete the point. To get this, I want to put the plane into a new collection. And to do this, click on the plane, press M and click new collection and name this collision or anything what you like. This collision collection, we can drag that in from our list of objects into our geometry nodes. Set this from original to relative and to separate children. And these are now instances. So we also want to do a realize instances node so that we can actually do something with the actual geometry of the collection. To get the distance between the plane and each particle, we can add in a geometry proximity node. As the target, set the realize instances, and then we have a distance socket over here. And we want to say, okay, with a math node, set this on less than, and when we can say if the distance is less than a certain value, like 0.2, for example, delete the point. So let's add in another delete geometry node. And this one, we want to add that in between the simulation input and the join geometry. And as the selection, we put the less than node. And then you will see points are going to be deleted when they touch the plane. Let's replace each point with like a bubble of mesh, like that will look like a paint bubble, for example. So what we can do is we do an instance on points after the simulation output, And as the instance, we set an icosphere, and we set that as the instance over here, set it on subdivision on 3. And as the scaling, let's set it on 0.28, for example, like this, or maybe even lower, like 0.26, just what you prefer. And then if we shoot it like this, then it looks like real balls are shooting. However, paint bubbles will never contain their perfect round shape while in the air, right? So we're going to add in some displacement. Do this by adding in a set position node. And in order to make the set position work, we have to do a realize instances again. Set that over here, and as the offset, we want to control that with a noise texture. Set the color of the noise texture into the offset. Then you see this happens. First thing that's happening is it's like shifting diagonally up. To reverse this, that it's like staying on its own position, add in a vector math node. Set this from add to subtract, and set this on 0.5 like this. Now let's make this displacement a little bit less. So let's do a vector math node again. Set this after the subtract. Set this from add to scale and set the scaling on 0.1. Then you're getting this. Let's also set the scaling in the noise texture on 1. And then you will see you're getting a little bit of that like bubble effect. And you see they still get deleted. That's perfect. I'm going to move all of this a bit over there. I'm going to put the group input a bit over there, because right now we are going to create the splash effect. And for the splatter effect, we want to create that every time a bubble gets deleted over there, that a new point is added in right on that position, and that point is then going to scatter around a lot of other points. So to add in points right on that position, we want to add in another simulation zone. And we connect both simulation output with the simulation input. And let's do a join geometry so that we can join the balls with the new points. If we do a join geometry node right over here and we connect the simulation output over there, then we're getting this effect. Each point gets duplicated like on each frame. It's not in movement, it's standing still, but it's like it stays there. We don't want to add in those points. We only want to add in the point that is like this one, that is close to the mesh. To get this, we can add in a delete geometry node. And as the selection, we can basically do the same thing as we did before with this geometry proximity, realize instance, collection info, and the less than. Because with this, we can like calculate the distance between the points and the faces. So let's take these nodes, Shift D to duplicate them, and move them over here. Set this from less than to greater than, because we want to delete everything except for when it's like touching it. And then connect it with the selection. And now you will see it starts adding in points right where the bubbles are touching it. You can clearly see that some points are kind of like floating above the plane. We don't want that. We want them to always stick to the plane. So in order to do this, we can add in another set position node after the join geometry. And we've actually got this position of the plane in the geometry proximity. So we just connect this position with the position of the set position. And now if you press play and I move this a bit around, you will see they always stick to the plane. When you play the simulation, you see that a point is also added in over here. That's the beginning point of our simulation. We don't actually want that to be there, and the reason why it's there is because we're also connecting the simulation output with the directly to the simulation input over here. We actually don't have to do that. So if we disconnect this and we play again, then that point is gone and the simulation just works even better actually. I don't want that those points that we're adding in stay there forever. I want that they are deleted actually after a very fast time, like after 2 frames already. Because otherwise the splash will take like forever to finish. So we just want to have like a splash that happens in 2 frames. To get this, we want to track the age of each point. And to track the age of each point, we go to this simulation input. We click on this plus icon to add in a new attribute. Make this the age attribute. And we're not going to make this geometry. We're going to make this an integer. At the beginning, the age is 0. And if we connect it over here, then it stays 0, of course. If we add in a math node in the middle, every frame we want the age to be added up by 1. However, this doesn't work yet. In order to actually track the age of each particle, we want to capture the age of each particle with a capture attribute after the join geometry like this. Set this from float to integer, and then you can put the age into the value and the attribute into the add node. And now it's actually getting tracked. And with this, we can say, okay, if the age of a point is higher than a certain value, delete it. To do this, add in a new delete geometry node. Add that before the join geometry. And as the selection, we want to do a compare node. Set this from float to integer. And we want to say, okay, if the age is higher than, let's do for now, for the example, 6 frames. Higher than 6 frames, the geometry should be deleted. And now if you press play, you will see that is the case. I'm not going to set it on 6 frames, of course. I'm going to set this on 2 frames because we only want a short splash. Next step is that I want to replace each point with an object that can actually scatter around a lot of points. So kind of like a ring. And you might be surprised by how we are going to create this ring, but we're going to create it with a curve line node. And if you connect this with the join geometry as well, then we can actually see what we're doing. This curve line node, we want to do a curve to mesh. And as the profile curve, we set a curve circle. You connect that over here, and you see we're getting this. In the curve line, we can set the Z on 0.1. And for the rest, we don't have to change anything. It's fine like this. To replace each point with this object, we can add in an instance on points nodes again and set it as the instance. Then you see it's added in like this. We can now also disconnect this curve to mesh from the joint geometry. 2 things that I want to change: the rotation and the scaling of this circle. For the rotation, I want that it's like be affected by the normal of each closest face. So to get the normal of each face, we can take our collection info and realize instances again and shift D that to over here. And to find the closest face, we can do a sample nearest node. And to find the normal of that nearest face, we can do a sample index node. Set both on from point to face and set the sample index to vector, because the normal that we want to capture is a vector. Connect realize instances with both geometries and set the index of the sample nearest to the index of the sample index node. And the value, this vector value, should be a normal, since we want to capture the normal data of each face. If you now connect this value to the rotation, then you see, yeah, that doesn't look good. That's because we have to do an align Euler to vector node between these 2 values and set this value onto a vector. And then let's turn on Z. And then you will see it will always be rotated according to the face that it lands on. For the scaling, I figured it would be good if it's like always half of the scaling of a bubble. So what we're going to do is we're going to the instance on points nodes for the bubble. So this one. And we're going to add in a value node. And this value node, we set this on 0.26, the same value as we have over here. Connect that with the scaling. Now if you connect this value node also with the scaling of the instance on points of the circle, then you see now it's always the same scaling. But we don't want that. We want to have it half the scaling. So we add in a math node and we connect that over here, set this from add to divide and divide this value by 2 so that it's always half of the scaling of the bubble. Let's create a lot of points onto this circle by adding in Shift A distribute points on faces node. Set this on a high value like 1000 for example. In order to make the simulation work, we want to add in a realize instances node over here. Set it then on 5000. So that it's more dense in points. To push out these points along the normal of that circle, we want to add in a 3rd simulation zone. So let's do that. New simulation zone and connect the distribute points on faces with the geometry over here. Disconnect the distribute points from the joint geometry and connect this one with the joint geometry. We want to push these points out of the normal, so the beginning velocity of each point is going to be the normal direction of each face. And we've got that data over here in the normal socket. So we connect that with the simulation input and then also with the simulation output. And then if we do a set position node and we connect that with the offset, let's see what's going to happen. Nothing. One of the things that we have to do is we have to capture this normal data for each point. So we have to do a capture attribute again. Set this from float to vector. and we want to capture the normal data for each point and connect it like this. Now another thing, it will still not work by the way. Another thing that we have to do is we have to add to each frame new normal data. So if we do a vector math node again, and we do that over here, and what we want to add is the same normal, but scaled down. So if we do another vector math node, and we set this from add to scale, and we scale this with a factor of 0.2, and then we connect that with the add, then we're getting this. We have to do a little bit more stuff, because it's still not working. I almost forgot that we're not adding in new points on each frame. So we have to do another join geometry node after the set position, and we have to connect this capture attribute with the join geometry. Then we're getting new points, and then it looks like a splash already. However, they are now going into oblivion like infinitely far. We don't want this. We want them to start very fast and then slow down until they stop. To do this, we can divide the velocity by a factor of 2 on each frame. So let's duplicate this vector math node, set this from add to divide, and set all the values on 2. Then you're getting this. They are now going in a perfect circle, right? That's because every point gets the same velocity. But a splash is very random. So we're going to give every point a random velocity by randomizing this scaling factor over here with a random value. Connected with the scale, and then you're getting this. You also see that each splash is now perfectly the same distribution, and that's also impossible in real life. So to randomize this per frame, we can make the seed in the distribute points on faces dependent on the scene time. So let's add in a scene time node and connect frame to seed. And now each splash is going to be random. Another thing is, you see it's now splashing like on this corner of the plane. And then you see it looks, yeah, it doesn't look good, it stays flat, right? But it will look better if it will bend with the faces of the plane. To do this, we're going to take this collection info, realize instances, and geometry proximity, shift D that to duplicate that to over here to all the way on the end of the geometry nodes. And if we then do a set position node after the simulation output, and we connect position with the position of the set position, then it will bend with it. Now the splash still consists of only points. But let's make it look like real paint. So we're going to convert these points kind of like to meshes. And we're going to do this by first converting it into a volume actually. So let's press Shift A and do a points to volume node after the set position. Then you see it becomes like a cloud thing. And we want to convert this volume into a mesh. So let's do a volume to mesh node after this. And then we're getting this. It's a bit too much paint or slime. So we're going to scale this down a bit. What we're going to do in the points to volume, we're going to set the resolution from amount to size. And let's set the voxel size on 0.05. So that we have more resolution on our mesh. As the radius, you see if we set this lower, we're getting more like paint-ish things. But I think it would look cool if we can randomize this radius so that not every point will be as big, because like with splattering around, it should all be randomized. So let's add in a random value node, and let's set this random value node as the radius of our points to volume node. And let's set the max value to like 0.1 or something like that. Then we're getting this. One final thing that I want to create is that when the points are going to be splattered on a face that is like going downhill, that has an angle, that the paint slowly slides down, as if there would be gravity on it. So to do this, let's add in some gravity. So let's do a vector node. And for this vector node, let's set this on minus 9.81 again. And then let's duplicate this vector math node by pressing Shift D and putting it over here. And let's put this vector into the add node. And then this happens. Yeah. The gravity is way too strong at the moment. So what we're going to do is we're going to scale this down a bit. Take this add node, Shift D to put it over here. Set it from add to scaling. And if we then set the scaling on 0.01 or something, it will already go slower. But before we change like the scaling to the optimal value, I want to do something else. I want to make it that points that have a smaller radius are falling down slower than the points that have a higher radius. So to create this, we're going to get the random value that creates the radius. We're going to put that over here, and we're going to connect this with the scaling of the scale node. Then you will see it will go way too fast again. So let's scale down the random value that goes into the scaling with a math node and set this from add to multiply and set this value on 0.001. Then you see it goes very slow. Well, what you could do as well is set the vector not on -9, but like on -50 or something like that. Then you will see it will already start to be a bit more realistic. You have kind of like control over how fast the fastest points go and how slow the slowest go. This is basically it for the geometry nodes. The only thing that we could do is like a set shade smooth to make it look smooth. Also the balls will look smooth like this if you put that after the join geometry. Plus we can also add in a material for this. So let's create a material by splitting our screen in half. And set this on the shader editor, create a new material, name this like slime or something like that. And let's also go into the material preview. You'll see if I change the base color, nothing will happen. That's because in the geometry nodes, we have to assign the material to this object. So let's do Shift A, set material after the shade smooth and set this on slime. Then you see it works. I like to set this material with a very low roughness. For the color, I really like the green one, but to be honest, it's all up to you, of course. You should take a look at what looks the best in my scene. To me, the green one looks the best at most times. And then you see we've created a pretty cool simulation. And the cool thing about this is that we add in a new object, like for example a monkey, and we position that over here, and we give this a subdivision surface level of 2. If we now add this monkey to our collision object by pressing M, then if we press play again, you will see you can also splatter on the monkey. And that's pretty cool. So there we have our slime shooting splattering system. If you like this video, please give it a thumbs up. Comment down below if you have any questions. And if you want to help out the channel, please consider subscribing. And with that being said, I see you in the next one.